Greetings. So let's continue this subject with the logic programs part. So this video is just about the logic programming part, and let's give a title. So the function TP, function T is for transformation, P, and here P is a program, is a logic program. So for different programs we will have a different function. So let's just start with an example. Our sample program is using the variables P, Q, R, S, T. Now remember, these are from this point on simple propositional variables, so they will take either the value 0, false, or the 0, 1, true. So, and we only have 5 variables just to keep it simple, and the set of clauses in this program is okay. So first let's just use the P implies Q. So remember, clause only have positive variables, so there is no negation. Consists of a single implication with a single variable on the right hand side. This is the Q in this example, which is called the head of the clause. So just as a memo, this guy here is the head of the clause, and that guy there is the body of the clause, right? And in the body there can be a finite number of variables. So for example, if you wish, you can just add the P and T implies S as a clause. Okay, this is not as an S as it should be. Yeah, that's great. So on the left hand side in the body there are always conjunctions P and T. So, and for example, we can have the T to S as well, and we have the T to Q as well, and we have the P to R, and actually the left hand side can be empty, so it's just nothing implies P. Well, nothing is not an entirely good word, but we will take this later. 1, 2, 3, 4, just one guy is missing from the example, so this is the same example as the one in the lecture notes, of course, that's why I'm but the order is different. So here we have this okay, so just cool. Now, and we should give a model for this program, and as we've already discussed, the variable assignment, which just sets all the variables to 1 to true, is always fine, because on the right hand side there is one variable and the implication is always true if the right hand side is true. So so that's why it's always a solution, but we seek for a minimal one. So you just set only some items to 1 which are necessarily set to be 1. Now, for example, you can come up with the following algorithm. So first set all the variables to 0, P, Q, blah 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 to 0, and you will have a current variable assignment. Then while the assignment is not a model, we just recompute all the bodies, so just evaluate all the bodies. And then if a body is set to 1, then it means that the implication has a true left-hand side, and in order to satisfy the implication, you have to set the right-hand side of the head to 1 as well. So if it closes body is true, is satisfied, then set its head to 1 in the new assignment. And you are just repeat, evaluate, reassignment, evaluate, reassign. I'm just zooming out a little bit just to make this visible. So that's fine, that's an algorithm. Just compute, recompute, and recompute all those assignments. And I will do this, but I'm trying to move this guy to the right in order to make the actual program visible. So I'm just moving this guy right, but I'm almost sure that you already understand what the algorithm does. And then in the middle I will track our actual assignment in a tabular form. So the columns will be indexed by the variables p, q, r, s, and t. And in the first round, each of these guys will be set to 0. That's just initialization. Yeah, this guy. And now I am just recomputing all the bodies. Now everything is 0, so, and we are just making conjunctions. 0 and 0 is still 0, false and false is false. So it might seem that nothing gets evaluated to 1, but it actually does, because here in this clause we have an empty conjunction, and as we've already discussed, an empty conjunction does evaluate to 1, because this is just the infimum of an empty set. If you view this as poset theoretic stuff, but well, you can define the empty conjunction to be 1 and the empty disjunction to 0 if you wish. It's the same thing, same underlying principle. So because of this clause has a body evaluated to 1, hence in order to satisfy this clause we have to set the p to 1, right? So in the next round p is 1. Now for all the other clauses we have zeros currently, using this implication, using this assignment, so no one else should be set to 1. So all the other guys are remaining zeros. Now in the next round we are just re-evaluate all the bodies, and of course this body here is still 1, so in the next round we still have to set p to 1. I'm just doing that, but under our current assignment, this guy here, I'm just using circles to denote something is 1 in our current assignment, so these guys are 1. Now this means that the very first clause, p to q, has a true body, which means that I have to set this guy to 1 in order to satisfy this clause. So if a clause's body is 1, then set its head to 1 as well, which means that q should be set to 1, and also r should be set to 1 because of this clause. So this clause and those The two clauses have at this point, at this very moment, true body, which means that their head should be set to 1 as well. Now, currently we don't have any more clauses using this assignment, so we are not just think about it as doing these in parallel, right? So I'm always using only the previous row's entries, and the updates will be migrated to the next row. Now, again, using this third assignment, what do I have? So P is 1, Q is 1, Q is 1, and R is 1. Now on the left hand side, well, okay, so this Q is also 1. You can mark this guy if you wish, but it doesn't really matter, because this part here says that if the body is 1, so you want to check the heads. But in this guy here, P and Q to S gets evaluated to 1, its body, so we should set S to 1. And also this guy here is still 2, it's worth mentioning that these guys are still true. The bodies of these guys are still true, so it seems that if you set something to 1 once, then it will remain 1. And actually this is a fact. So right now we have 1, 1, 1, and because of this guy here, the last one, we should set the S to 1 as well, and then T can be 0. Now again, if you just recompute, T is 0. Okay, you can mark all the occurrences of S right now, but these new marks won't enforce more assignments, so these 3 clauses still have a false body in our current assignment, which means that I have to set Q, R, P and S to 1, which is fine. 1, 1, 1, 1, nothing's changed, so it seems we just reached a so-called fixed point of the computation, which is just a value which keeps remaining the same after many iterations. But if you just check this, and then this and this and this clause gets satisfied, because, and this as well, because their head is 1, and these 2 clauses get satisfied because their body is 0. So an implication is true if its body is 0 or its head is 1, which means that this is a model of a program. And actually this is the least of the program, so no matter how you try, you won't be able to reduce the number of ones in this model, so you cannot change any of these 1s to 0s without breaking the model. Now that's fine, and let's just formalize it a little bit. So what we've just done here, so this function, this row-to-row transformation, so you just take a row, and from these values you just compute new values. So there's basically a transformation of assignments. A row is an assignment, it's a complete assignment of the variables. So this row-to-row transformation if the program is called P, then is called T, like transformation indexed by the program itself. So if you call your program Q, then it will be TQ. If you call your program, I don't know, S, then it will be TS, whatever. So is this index, the subscript, is the program itself. And formally formally, and I'm just moving this guy up. So we have a TP function, a function TP, which takes an assignment and outputs another assignment, or the same assignment. So it maps assignments to assignments. Remember, an assignment is just a mapping from the set of variables to the poset 2, which is denoted by 2 to the z, so it's fine. And usually an assignment will be denoted by small u, v, w, stuff like that. So how this function is defined. So TP is a function. It gets an assignment, outputs an assignment, and an assignment is given by the value of the variables, by the values of the variables. So I can just say that. Now what's this? TP is a function. U is an assignment, which is also a function. Doesn't matter. TPU is an assignment which gets a variable and outputs a value, a bit, 0 or 1. So TPU of Q should be the new value of Q, of the variable Q. So while U here in this formula is the old assignment, the input assignment, TPU is the new assignment we just create. Q is a variable and TPUQ is the new value of Q, of the variable Q. Now how should we compute this? Well, the saying was, first we evaluate all the bodies and set those heads to 1 for which there exists a clause with a body evaluating to 1, which means that in order to get the value of Q, we should collect all those clauses having Q as head. Yeah, okay, so we just collect all those P and blah 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 and P and to Q. The important point here is this is the same Q. So you are just collecting in P all those clauses of P having Q as head. You just evaluate those bodies, which is written as UP1, right? UP1 is the value of P1, of the variable P1 in the old assignment, according to the old assignment, and the UP2 is the old value of the second variable, and so on, and UPN. So this is just the value of the clauses body, and if any of them gets evaluated to 1, then Q should be set to 1 as well, which is just a supremum or disjunction, if you prefer to call this that way, because if there is anybody evaluated to 1, then this result will be 1, and if all the guys are evaluated to 0, then this result will be 0. So that's just a supremum, that's just a disjunction. Okay, so TPU of Q should be a quite large disjunction. Now this is an important formula. We will have so much fun with this guy, because the important thing is regarding this function is the following statement, and I will prove this. Statement U from 2 to the z, so it's an assignment, is a model of P, right? We are just seeking for models, so it's important to determine what can be a model and what cannot be a model. And the statement says that this holds exactly if the TP of U is smaller than or equal to U itself. in all coordinates. So let's just get back here. Here I applied the dp function. Now it increased. Okay, so it's not a model. And then again I just applied the function dp, and again the 1000 became 11100. It's an increasement, not being smaller than or equal to, so it's the other way around, right? We need this. And it's not that, it's just increasing coordinate wise. And again we had an increasement, but at this point we had equal assignments. Equal is fine, because if TPU equals u, then TPU is less than or equal to u, so it's fine. Now let's say statement that as soon as we got one single row u for which the TP function just resulted in a smaller than or equal to, in this case it was equal, assignment, then we can stop, and because this is a model. Now let's prove this. Proof. Of course, one way to prove that is just to prove that if something is not a model of P, then and only then TP of U is not smaller than or equal to U. Right, so this is the same. So we have an equivalence, and we are just negating both sides of this equivalence. Then it's stated the very same thing, because there are only two values in the logic. So what does this say? U is not a model of P. This means that there exists one clause, at least one clause, which applies to false under U. So there exists some clause, some P1 and P and Q in P evaluated to false under Q. So I can write this, so with say the U of P1 and Pn to Q being false, being 0. So this clause is false. Now, how can an implication be 0? It can be 0 only one way. So it's just the left hand side, the body of the clause should be evaluated to 1, while the Q should be evaluated to 0, the body, right? This is the only case when the implication becomes false. And if a conjunction here in this body is 1, then it means that each of these guys are 1. So basically we have that there exists a clause Pn to Q in P such that U of P1 is the same for these P's, U of Pn, this is 1, and the U of Q is 0. Yeah. Now this is equivalence, so this basically says that not a model means there is a clause which is false, and there is a clause which is false means that there is a clause for which the rest of each of these variables occurring in the body of the clause are 1, while the head of the clause is 0. So we have this guy here, and let's continue with this TPU being not smaller than equal to U. So not smaller than equal, and these are functions, means that there is one coordinate on which the direction is the other way around, because here we have only two values, 0 and 1, and they are ordered. So it can happen only in that case where there is a variable on which TPU is strictly larger than U. So this means that so not being smaller than equal to means that there is some Q for which the TPU of Q is not smaller than or equal to the U of Q. Now, how can it be so? This guy here is a member of 0, 1. This guy here is also a member of 0, 1 with the standard ordering, so I should have written that these are members of the poset 2. And this means that this guy here should be 1 and this guy here should be 0, because there is no other way they can be in this relation. So basically, evaluating an implication is just saying that the left hand side is a lower bound of the right hand side. You can view this as an upper bound, lower bound comparison. So okay, so we have this, there exists a Q for which the Q is 0. Now, how can this TPU be 1? Now, if the TPU is 1, TPU of Q is 1, then it means that this junction, where you just collect all those clauses having Q as head, and you just evaluate these guys, this is 1, because that was the formula TPUQ equals this expression, so that's why. Now, and so this means that this is also an if and only if arrow. Now, what does this mean? This means that this is a clause with Q as head, whose body gets evaluated to 1 because all the variables get evaluated to 1. So this again means that there is a clause P1 and Pn to Q in P such that U of P1, because this supremum evaluates to 1 if and only if there is an element evaluating to 1 in the supremum. If everyone gets evaluated to 0, then the supremum will be 0 as well. The empty set is also falling into this category, so the supremum of the empty set also 1, no, also 0, because that's the least element of the poset 2. So this means that this holds if and only if UPN is 1 and UQ is 0. And if you just view this from a distance, then these two guys are the same. These two guys are the same. Okay, right? So actually we have just proven that the assignment U is a model of the program if and only if TP transforms U into some assignment which is a lower bound of the original assignment. Now, that's fine, and for the next part we should just note that the TPU being smaller than or equal to U seems to be important. So we will just seems to be important. So basically this states that there is a poset, in this case the poset of assignments, of all the variable assignments, and we are very interested in a point U of the poset which gets transformed by function f to smaller than or equal to value. So it's just f of x being smaller than or equal to x in general. Here TP of U being smaller than or equal to U, but it doesn't matter how you name your functions and variables. So basically we are very interested in functions which map a poset to itself, And if we have such a function, we are very interested in computing a single point in the poset, say u, for which the value of u under the function, so f of u, dp of u in this case, is smaller than or equal to this u. Now these points will be called prefixed points of the function dp, but that's a math part only, and I promise that this video will contain only logic parts, so I'm just stopping the recording now, and in the next video we will just have math and some thoughts on prefixed points of functions. Till then, bye bye.